Welcome to this explainer. Today we're going to tackle one of the absolute most fascinating questions in modern science. How exactly does dead metal become intelligent?
I mean, just look around you. Your smartphone, your laptop, even your car. They all seem to think, right? But how does a computer actually make decisions? How do billions of microscopic transistors somehow turn into the incredibly smart devices we rely on every single day? Well, it all starts with digital electronics.
Okay, let's dive right into this. We're going to take a bottom-up journey today, starting from simple ones and zeros all the way to complex robotics. We'll cover the language of computers, meet the logic gates, building complex circuits, adding memory and clocks, and finally, powering the modern world.
Section 1. The language of computers. Let's transition into our first step here, which is really just understanding the raw, fundamental electrical signals that make up the vocabulary of computers.
To really get computers, we have to understand why digital signals completely took over. In the past, we relied heavily on continuous analog waves. The problem, though, is they are highly prone to noise and signal distortion. Basically, if an analog signal degrades, you lose information. But on the digital side, we have discrete square pulses. They don't deal in maybes. They are clean, distinct, and easily regenerated. Even if a digital signal gets a little noisy, the computer can still clearly read that underlying pulse.
And that brings us to 0 and 1. Now, these aren't just abstract math concepts. In a physical computer circuit, these two binary digits simply represent distinct voltage levels. A 0 is a low voltage state, meaning off or false. A 1 is a high voltage state, meaning on or true. It's wild to think about, but every photo you take, every text you send, is ultimately just billions of these tiny high and low voltage pulses rapidly turning on and off. Section 2. Meet the logic gates. Now, this brings up a massive question. How do we actually calculate, process, and make decisions with nothing more than those simple zeros and ones?
The answer lies in Boolean algebra. This is mathematical logic using only true, or 1, and false, or 0, to represent real-world states. Think of a simple light switch in your home. It's either on or it's off. Or a door lock, right? It's either locked or unlocked. Boolean algebra gives us the mathematical framework to take those simple true or false states and start applying logic to them.
We actually apply this math using physical components called logic gates. Let's start with the AND gate. The rule here is strict. It outputs true only if all its inputs are true. Imagine a high-security bank vault that requires two managers to turn their keys at the exact same time. If manager A turns their key, but manager B doesn't, the vault stays shut. It's a 0. Both keys literally must be a 1 for that door to open.
Next, we have the OR gate and the NOT gate, which basically round out our fundamental decision-making toolkit for this explainer. An OR gate is way more relaxed. It outputs true if any input is true. Think of a modern car with a door ajar sensor. If the driver's door is open or the passenger's door is open, that dashboard light turns on. The NOT gate, on the other hand, is kind of the rebel of the group. It simply inverts the input completely. Send it a 0, it spits out a 1. Send it a 1, you get a 0.
And this brilliantly illustrates exactly how these inputs map to outputs in practice. If input A and input B are both 0, both the AND and the OR outputs are 0. But look what happens when A is 0 and B is 1. The AND gate outputs 0 because remember, it strictly needs both to be true. The OR gate, though, it happily outputs a 1. It's only when both A and B are 1 that both gates fire and give us a 1. This simple routing of electricity is the absolute foundation of machine decision-making.
Section 3. Building complex circuits. So we've got these simple truth-testing gates, but how on earth do we scale them up to perform actual binary arithmetic, like addition and subtraction?
Well, before we can build calculators, we need to talk about universal gates, specifically NAND and NOR. These are the ultimate Lego bricks of digital electronics. By just stringing together enough NAND gates, for example, you can physically construct an AND gate, an OR gate, a NOT gate, or literally any other logic gate in existence. They form this incredibly flexible foundation for modern microchips.
The math itself happens in sequential steps, forming what we call combinational circuits. Step 1, we connect our individual logic gates. Step 2, we arrange those gates to form something called a half adder, which can actually add two bits together and calculate a carry bit, just like carrying a 1 in basic math. Step 3, we combine those into full adders, handling much larger sequences of numbers. And finally, step 4, we cascade these all together to build multiplexers and full-blown calculators. The data flows through these blocks practically instantly,
literally turning raw voltage into complex math.
Section 4. Adding memory and clocks. Okay, so our circuits can now do math, which is awesome, but we hit a massive hurdle. Calculating is great, but how does a computer actually remember the answer it just came up with?
To solve that, we introduce time into our circuits using a clock pulse. This is a continuous square wave signal that synchronizes operations right across a digital circuit. You can really think of the clock pulse as the heartbeat of the computer. To put that into perspective, when a modern processor is running at 3 gigahertz, that means this clock is ticking 3 billion times every single second. It ensures that data moves exactly when it's supposed to, keeping billions of moving bits perfectly synchronized.
By combining that clock pulse with our logic gates, we create sequential circuits. The formula here is super cool. Sequential circuits equal combinational logic plus memory. We achieve this memory using components called flip-flops. A flip-flop basically locks in a 1 or a 0 and just holds onto it, acting as fundamental bit storage. This allows the circuit to remember previous states. It's the critical difference between a basic calculator that forgets everything the second you let go of the button and a modern computer that can store programs, files, and massive operating systems.
Section 5. Powering the modern world. Let's move to our final section and zoom out a bit to see how all of this builds the big picture of our modern lives.
I want to walk you through this flowchart because the evolution of complexity here is just staggering. We start at step 1 with basic digital electronics, those tiny logic gates and flip-flops we just talked about, but package millions of those into a single chip and you hit step 2, microcontrollers. These are essentially tiny, self-contained computers. Program those microcontrollers to do specific jobs and you reach step 3, embedded systems. Finally, push this architecture to its absolute limits, stringing together billions of logic gates, and you arrive at step 4, cutting-edge AI and robotics. Those simple ones and zeros literally scale up to become incredibly intelligent systems.
Because it scales so perfectly, digital electronics are everywhere. We're talking smartphones, laptops, the navigation and drones, the ECUs that manage your car's engine, AI hardware, satellite systems, and life-saving medical equipment. And hey, from a career perspective, mastering these basics opens doors into massive industries like the Internet of Things, embedded systems engineering, and advanced chip design. Every single one of these fields relies entirely on the core principles we've covered today.
So we'll leave you with this thought today. Master these fundamentals and you'll understand the language that powers modern technology. The next time you pick up your phone or see a drone flying overhead, just remember what's really happening inside. Beneath the sleek screens, it is just millions of tiny digital logic gates, rapidly flipping between true and false, 0 and 1, speaking the fundamental language of the future. So as we string together trillions more of these gates in the age of AI, what will they learn to do next? Thank you so much for joining us on this explainer, and we will see you next time.